Now, we're going to talk about something called the sampling distribution of differences. And this is actually a topic that is really important for you to understand inferential statistics. And it's one that you want to make sure that you do get before you move on. So if you review this section a couple of times, and if you read about it in the book and you're still perplexed, please let me know, or the stats TA, just let us know so we can help you. But it is important that you struggle first. All right, don't read it once or listen once and say, that's it, I don't understand. You won't benefit from our help until you have struggled with this a little bit. Now, if you're in tears, you're probably struggling too much. This should not make any of you cry, okay? And in fact, a lot of you are going to get this just first time out of the starting gate. It's going to make sense to you. But if you're not one of those people, I don't want to see you cry. That doesn't, bode well for my reputation. So please just come and see us if you get to that point. All right, now I don't expect anybody at this point to understand what the definition means. I'll read it out, but we're going to come back to it. So what is the sampling? Remember this, a distribution of an estimate. The sampling distribution of differences. It is a distribution of the difference between two sample means, so 2 X bars, taken from 2 samples, which are derived from 2 populations, where mu1 equals mu2. Get it? No? Okay, don't worry. What is it saying? First of all, you have to have 2 populations. Population 1, population 2. Let's say this is the population of men, the population of women. I'm just going to stick to that because, we can all, I think, relate to that. All right, so here we have all the men in the world and all the women in the world. Well, we have to start off assuming that they're identical. Now, that means that their means will be identical, right? Mu1 equals mu2. Now, you might be saying, Lynn, I know for a fact there are differences between men and women. One is from Venus, one is from Mars, that sort of thing. I'm going to say it doesn't matter. Just like, you might be sure that somebody committed murder and you've got all the evidence in the world, but you still have to start off by saying innocent until proven guilty. So just like that, we are going to assume that these are identical. So men are identical to women, which means mu1 equals mu2. Now, what you're going to do is you're going to draw a sample from each population. And it has to be the same size. So if you take 10 men from this population, you have to take 10 women. If you take 20 men, you have to take 20 women. All right? So you're going to decide on a sample size. And you draw a sample from the population of men, and you're going to calculate X bar, right? So this will be the sample mean for the men, okay? Same thing here. You're going to take a sample from the population of women, and you're going to calculate the sample mean for the women. Now, if there were no sampling error, zero sampling error, well, this sample mean would equal mu, right? If there was no sampling error, this mean, the sample mean for men would equal the population mean for men. Same thing over here. If there was 0 sampling error, then this X bar would equal its mean, mu. So this sample mean for the women would equal the population mean for the women. But of course, we know that it's not a question of if, it's a question of how much. So this X bar might actually, come from this side of the distribution. Maybe this X bar is going to be over mu. Maybe it's going to be under. Same thing here. This X bar for the women, maybe it's going to be overestimating mu, maybe it's underestimating. We don't know, but chances are that we do know. What we can count on is that this X bar is probably not going to be equal to mu, and this X bar is probably not going to be equal to mu. So let's go ahead and say, well, okay, let's subtract them, all right, to see just how different they are. So what we do? All right, we're going to subtract what we got for the men and what we got for the women. And guess what? We're going to plot it on another distribution that's going to be on the next slide. All right, but I want to stick to this slide because guess what we're going to have to do? We're going to have to go back and get another X bar. All right, same sample size. Don't change your sample size. Get another sample of men, another sample of women, subtract, oh, dang it. Sorry. Subtract them and then plot it on the next distribution. Guess how often you're going to have to go back and get samples until you have exhaustively sampled. All right. So that means you're going to get a lot of differences between the men and the women, the samples. Because ultimately what we're trying to do is we're trying to figure out if men and women are different. We start with the assumption that they are identical. All right. If they weren't identical and we subtracted mu1 versus mu2, we would know men and women are different, right? If they didn't start off as equal, if these two were different, we would know for a fact that they're different. But we don't know for a fact that they're different. We're going to start off with the assumption that they're the same. And then we're just going to keep getting X bars from here, X bars from there, and see how different the sample means were. Okay, so we're going to plot these differences after we've exhaustively sampled. And this is called the sampling distribution of differences. So sometimes when we subtract our two sample means, it's going to be less than the average of all these numbers, right? Whoops, dang. Sorry, I don't know why. I guess I tap too hard sometimes. All right, so let me rephrase that, or let me explain something and then go back to that. So this distribution, you're plotting all your X bar 1 minus X bar 2. Okay, so you're plotting all these differences. This is simply the mean of all these numbers. So it's mu sub X bar 1 minus X bar 2. This is just a reminder of what this is a mean of. So again, on the x-axis, you've got all your differences between your two sample means, and this is the mean of all these numbers. So sometimes anything on this side, this means that on these occasions, X bar 1 happened to be smaller than X bar 2. So the mean for men happened to be smaller than the mean for women, and you got negative answers. And this one just happened to be that if you're on this side of the distribution, the mean for men was higher than the mean for women, and that gave you positive answers. But this is hypothetical, right? We don't actually exhaustively sample from each population and subtract sample means. It's a theoretical distribution. So it's hypothetical, and it would be normally distributed. So what that means is that half of these differences are going to be negative answers. Half of these differences are going to be positive answers. So if you average out the negatives with the positives, guess what you're left with? Think about that. This is the average, the mean of all these numbers. The mean is the center of gravity. So if you have negative numbers here for differences, right? Differences between sample means. If these are negative and these are positive, when you average them all out, the mean is the center of gravity, and you are left with 0. 0. Okay, mean is the center of gravity. Now, what about this question? Would the sampling distribution of differences exist if there was no sampling error? No, it wouldn't exist. Why? Because X bar 1 would always equal mu1. There would be no sampling error. x bar 2 would always equal mu2. There would be no sampling error. So if mu1 equals mu2, when you subtract them, what are you going to get? 0, right? We said mu1 equals mu2. That was on the previous slide. We're going to assume that there is no, that they are identical. And if there's no sampling error, that means x bar 1 is mu1, x bar 2 is mu2, and when we subtract them, we get 0. So we know that there's going to be sampling error. We know that sometimes the amount of sampling error here is going to be large, and it's going to be in the tail of this distribution. And in this case, again, it just means x bar 2 happened to be bigger than x bar 1. Over here, if we look over at this end, we would say, well, we know that sometimes x bar 1 and x bar 2 are going to be very different from each other, and that's going to put them out in this tail. And this just is positive because this mean happened to be larger than that mean. But we can also say that most of the time, though, when we get x bar 1 and x bar 2 and subtract them, if it is true that the two populations are identical, that means that most of the time we can expect to get small differences between x bar 1 and x bar 2. They're going to be very close to 0. They're going to be small differences. That's going to happen more often than not, but only if our original assumption is true. If it is true that mu1 equals mu2, that means we're going to get, most of the time, differences here between sample means are going to be small. So, from the sampling distribution of differences, we can find the probability of getting a difference of any size between two sample means, like men and women, from two populations that supposedly have the same mu. So we're saying, we're going to initially assume that men are no different from women. All right? Okay. But when we sample, we know we're going to have sampling error. So if we calculate the mean for men and the mean for women in our samples, we're going to have sampling error. But at what point are we going to say that those two sample means are so different from each other, it's probably not sampling error anymore? Well, what we're going to do is when we could do this theoretically, is we get this sampling distribution of differences. Remember, I just showed you how to do that. Okay, so exhaustively sample from each population, calculate x bar 1, x bar 2, subtract them, and plot them here. Now, again, if mu1 equals mu2, if the population of men is identical to the population of women, that means that when we subtract x bar 1 minus x bar 2, we should get a very small difference. All right, if in fact the two populations are the same. But just by chance, we could get very large differences between x bar 1 and x bar 2, right? By chance, we could get a very large difference between x bar 1 and x bar 2. But that doesn't happen very often. When mu1 equals mu2, we're more likely to see small differences between our sample means. Very small differences. That's what happens more often than not. Could you get a big difference? Yes. But if you're a gambling person, no judgment, but let's say you're a gambling person, go with the odds and say, you know what? This huge difference between, let's say, men and women could be under this distribution. It could belong here, and say this is just all due to sampling error. But it's so big, so highly unlikely, that what we're going to do is say that it probably does not belong here. It probably means our initial assumption was false. And you know what? there is a difference between men and women. But if you were to get a difference between men and women that is very small, then we would say, well, that's no big deal. We kind of expect that, right? Even when mu1 equals mu2, we know we're going to see differences between our sample means. And so as long as that difference is small, again, it's probably just sampling error. But if we get a very big difference, that's when we say, wait a second. It could just be sampling error, but what's the probability? See how small it is? So rather than say, oh yeah, that's just sampling error, we're going to say, you know what? It's probably the case that our initial assumption was false and mu1 does not equal mu2. Now, in this chapter, we actually are, not going to learn about a specific inferential test. That's going to come later, okay? But understanding this forms the basis for understanding inferential statistics. So if you get this, then you can get inferential statistics very easily. So what I would do is I would go back a couple of slides, review the definition for a sampling distribution of differences. And again, we're going to focus on the difference between sample means. But go back and listen and make sure that you understand, and you'll be ready for lecture 2 of chapter 6. And just to take to be with a wow, right, is again, if we see small differences between our sample means, then we're going to chalk that up to sampling error. We're going to say, that's, we have 2 groups here, 2 sample means. They're probably not different. It's probably just sampling error. But if we get a large difference between our 2 groups, we look at the means and we subtract them and we see that they're large differences, that is probably telling us that we have sampling error and something else. In other words, the means for our 2 groups are different, yes, because of sampling error, but something else is going on. And that's when we would say our initial assumption is probably false. These 2 sample means do not come from 2 identical populations. All right? This is a good place to stop.